we talked about why exponential growth is not a very good model for things sometimes, like the rabbits in the classroom overrunning us and killing us all. So we decided that logistic growth might be a little bit better. We had this equation dp dt equals kp times m minus p, where m we've called our carrying capacity, which is the maximum value for the population, the maximum population. So what we want to do today is solve this logistic growth equation for p, and then we're going to develop a generic formula for it so that you don't have to use this process every single time, because it is relatively unpleasant. So we're going to do it the most unpleasant way possible with the generic one to make life easy later. Sound good? Okay. So we have dp dt, which tells us that the variables that we are really concerned about here in this equation are p and t. I don't see any t in there. All I see is p, right? So we need to do what with it? How are we going to solve this differential equation? If the only variable that I have in there, p, is in the top of my derivative. Okay, so integrate it by putting dt on the other side. So we need to do a separation of the variables, right? Everybody good with that? Separate the variables? Separate the variables?
Good.
Yeah? Everybody good with that? Okay. So let's do that. dp over p times m minus p equals k dt. All good? Just like whenever we normally separate the variables, right? Except that this one's a little more irritating. Now we're going to integrate both sides of it. On the right-hand side, that should just become k times c plus some constant. Okay. Everybody good with the right-hand side being kt plus c? We have a lot of different letters here. It's going to be a mess. Okay. And kt plus c. Now on the left-hand side, how do I integrate dp over p times m minus p, where m is just some number? We're going to have to use exactly partial fractions. Noah said partial fractions. I don't know if you guys can hear him because he's not very loud. Partial fractions. I don't care. So we're going to use partial fractions. So let's first write this as, I'll just do it over here. We know that to turn this into a separation of the two different fractions, it's going to be a over p plus b. Yeah, I told you it's going to be a mess with all the letters. A over p plus b over m minus p should equal 1 over p times m minus p. Good news. We have one number. Look at that. We finally have a number in our problem. That's exciting. All right. So what are we going to do? We're going to multiply the a by m minus p, and we're going to multiply the b by p. So we're going to get a times m minus a times p plus b times p equals 1. Good? Okay. And we've got to keep in mind the variable that we're using in the problem is p. So that's like our x normally within our partial fraction decomposition. We're solving for a and b, but we got to think about constants on the left and constants on the right. And so we're looking for a, and we're treating m as if it's just some number, right? M is just the number that's in our partial fraction normally. So how are we going to set up the system of equations for this? The constant on the left should be what? Should be a m. That should equal 1, the constant on the right. And we also know that we have 0 x's, or sorry, 0 p's on the right, but on the left we have negative a plus b p. So negative a plus b needs to equal 0. Everybody good with that? Everybody here good? Everybody at home good with that? It's a little, it gets a little bit convoluted with so many different variables in there, but yeah, so you gotta be a little careful. What does a equal then? A is 1 over m, which gives us b should be 1 over m. Yeah? Everybody okay with that? Everyone's good? Okay. All right. So now what we've got over here is, instead of dp over p times m minus p, we're going to have the integral of 1 over m p plus 1 over m minus p times m dp. So there's my 1 over m that I put in for my a and for my b, and I still have my 1 over p, and I still have my 1 over m minus p. Everybody good there? At home, you're all good?
Yes.
Yeah.
All right. Now we need to integrate. Well, before we integrate it, what do the 1 over mp and the 1 over m times m minus p have in common? They have the 1 over m. So it might be helpful to us if we take out that 1 over m. So we're going to have 1 over m times the integral of 1 over p plus 1 over m minus p dt equals kt plus our constant. I think that's going to make things a little bit easier for us to deal with. We can integrate 1 over p and 1 over m minus p fairly easily, right? So let's do that. We're going to need a new page. We're still going to keep our 1 over m out in front. And then as we integrate, the integral of the 1 over p that we just had was natural log absolute value of p. And then we had also the integral of 1 over m minus p. Keeping in mind that the variable is p, this integral should become what? A negative natural log of the absolute value of m minus p. And that all equals kt plus our constant. All right, we've done the integration. That was the easy part. And now for the hard part. Hard part is we need to, number one, what is the first thing we need to do here? No. No.
Simplify
They said solve for
the
P and they said solve for M. Those are both wrong. Combine stuff is okay. We could combine stuff. What else? What do we need to solve for first? We need to solve for C, right? We got to find that constant in some way, right? So how do we find that constant? If, what's the only thing we know? If T equals 0, what is the population? Don't worry, it's not like it's going to become another variable. Oh, wait, it is. At the beginning, what is your population? It's the initial population, right? P naught. Right? So if T is 0, P is P naught. That's the only thing we know in general about any logistic differential equation. So if we plug in 0 for T, we need to put T equal to P naught. That'll allow us to get rid of one of our variables. It'll allow us to get rid of C, or one of our unknowns. Okay? So we're going to have 1 over m. We're going to have, and Jenna, no. Derek, no. Oh, somebody said to combine this, to simplify. That was Derek here in the classroom. So we can also combine these. So what is the inside of this thing going to become? First off, I'm going to replace the p's with p naught, but I can also use log rules to combine those together. So that could become 1 over m natural log absolute value of, well, since we're replacing the p's with p naught, it'll be p naught over m minus p naught equals our constant. Okay. Wonderful. So we're going to get rid of our constant. We'll let Ryan join class. You're late, Ryan. Okay. Let's start. Okay, I did record. Good. Okay. And so we got our constant. Our constant is a horrible mess. True? Sorry, but it is. So we are now looking at this. We have 1 over m times the natural log of the absolute value of, and I can combine these together, p over m minus p if I want to. Okay. Equals what? Everybody good there? I mean, not good because you don't want it to look like that, but as good as you could get. At home, you guys good? Conceptually, all right? Following along, no issues so far?
Yep.
Yeah. Cool. Anybody have a good idea of what we need to do now? What do we need to do? Now we're up to the final part, which is solve for p. Now we're ready to solve for p. And that's what we do with the differential equation, right? We integrate, and we separate the variables if we need to. We integrate, we find our constant, and we solve for our variable. We want to solve for p. So what should I do to solve for p? Okay, move some stuff around and exponentiate is what we got here in the class. That's good. What do you want to move around? Well, I want to solve for p, so I don't want to put more junk over on the left-hand side. I want to keep everything, I want to get everything to the right except for my p. All right, yeah, let's start by multiplying by m. That sound good to everybody? That's going to clear up that and allow me to exponentiate. So if I multiply everything by m, I'm going to get natural log absolute value p over m minus p equals mkt plus natural log absolute value p naught over m minus p naught. Good? At home, you guys good?
Yeah.
Okay. All right. And then the next step in solving this for p is we got to get rid of the natural log, which we do by exponentiating, right? So let's exponentiate both sides. Put an e there. Put an e there. And as we do this, let's think about these absolute values that we have on here, because the population is never going to be negative, is it? P is never going to be negative. And M, which is the carrying capacity, which is the maximum value of the population, is always going to be positive. And it's always going to be greater than P, right? Because as we looked at the other day, that logistic growth curve, right, it goes up like this, and it actually is reaching M is where we have that horizontal asymptote. So actually M is always bigger than P. So the numerator is positive and the denominator is positive. So this is always positive. And same with this. So the absolute values have become redundant if we think about the concept of what we're doing with logistic growth. So I'm going to eliminate all the absolute values right now also. Everybody good with that? Just to save me the 4 finger writing things on the board. Okay. All right. So e to the ln of p over m minus p is just p over m minus p. Agreed? I'm going to have to go back and forth between these pages. I don't remember exactly everything I have over there. E to the mkt times e to the ln p naught over m minus p naught. Right, that's how exponent rules work. And e to the ln of p naught over m minus p naught should just be p naught over m minus p naught. So really what I'm going to do is I'm going to put the p naught minus m p naught out in front of the e to the mkt. Everybody good there? So we got equal p naught over m minus p naught times e to the mkt. Beautiful. Still got a lot of variables, but it looks good. Everybody agree that looks good so far? Okay. All right, now we got to solve for p. Well, that's a little bit of an issue because we have p over the m minus p. So we're going to have to clear that m minus p out of the denominator. Yep. At home, good? Good?
Yeah.
Yes.
Okay, so we're going to clear that m minus p out of the denominator. So we're going to get p equals, if we solve for p. No, we didn't. Okay. P equals, and when I do that, I'm going to have a p on the right-hand side attached to a bunch of other crap. And I'm going to have to move that p with all that other crap attached to it back to the left-hand side to factor and solve. So I'm going to have to distribute this whole term to both the m and the minus p. So I'm going to do that all in one step. If you're not okay with the one step after we do it, I can go back and write it out, but I think we'll probably be okay. Okay. So the m is going to get multiplied by this. So I'm going to have m p naught over m minus p naught e to the m k t minus p times p naught over m minus p naught times e to the m k t. Good? Or no? All good? Okay. Then what do I have to do? I have to bring the minus p times p naught over m minus p naught times e to the mkt back to the left. Okay. So I'm going to have p plus p times, and in fact, are you guys okay with me factoring the p out in the same step? Are you guys good with that at home if I factor the p out in the same step just to save us rewriting all of this another time?
Yeah.
Okay. P times, so that factor the p out of the p, that's a 1. Factor the p out of all of this becomes 1 plus p naught over m minus p naught times e to the m t equals m times p naught over m minus p naught times e to the m t. Good? Or no? Good, good, good. All 4 of you here, good. All other 32 of you at home, good?
Yeah.
Okay.
Yes.
Effectively, we've solved for p. All we have to do is divide by 1 plus p naught over m minus p naught times e to the mkt. And we're done. Sort of. We're going to simplify. All right. P equals. All right. What? I don't remember what do we have? M. Hang on. No one's going to read it out for me. Perfect. M times p naught
Minus
e to the mkt. 1 plus. All right. Cool. Good or no? Okay. All right. Now you're going to bear with me here while I do a little bit of simplification that might seem a little bit counterintuitive. I mean, this is done. This is fine. You could memorize this and have that be the thing that you just turn it into every time. But that's a lot of things. I'm going to simplify it down so there's a little bit less. So the first thing that I'm going to do is I'm going to get rid of this p naught over m minus p naught that's in the numerator. So the way I'm going to get rid of that is I am going to multiply by the reciprocal of that in the denominator. So I'm multiplying it by this. So if I get rid of it here and multiply by the reciprocal in the denominator, that should be the exact same thing. Would you all agree? I hope. Okay. Multiplying by something is the same as dividing, putting it down here, by the reciprocal. Right? That's how you learn. That's the sort of how you learn how to divide fractions way back when you were like little children. right? It's almost the same. It's just kind of like instead of multiplication, it's division. Good or no? Okay. So I'm going to divide by the reciprocal, which means I'm multiplying by the reciprocal of P naught over M minus P naught into the denominator. So I'm going to, okay, good enough. So in the numerator, we're going to now have M e to the M k t. In the denominator, if I am multiplying by M minus P naught over P naught, I'm going to have to distribute that to both of those things, right? So first off, that's going to turn the 1 into an M minus P naught over P naught. Agreed? Everyone good there? Second, it's going to turn this M minus P naught over M minus P naught, when I multiply by the reciprocal of that, that's going to disappear. True? So I'm just going to get plus e to the M t. Good or no? Okay. Then I'm going to get rid of this e to the mkt that is up there in my numerator. And so all I'm going to do is I'm going to multiply by e to the negative mkt in both the numerator and in the denominator. Okay, so I'm going to multiply, I'll even write this down. I'm going to multiply by e to the negative mkt here. I'm going to multiply this by e to the negative mkt here. I don't know why I made that parentheses so small. And that's going to get rid of the e to the mkt that's in the numerator, because e to the positive mkt times e to the negative mkt should be e to the 0, which is 1. And it'll just leave me with an m up there. So we're going to have p equals m over. Go back to the other page so we can do it. All right. This e to the negative mkt that's in the denominator now gets distributed to both things. The e to the mkt and the e to the negative mkt will become a 1, just like they did in the numerator. So we're going to have 1 plus m minus p naught over p naught times e to the negative mkt. And that's what we're going to solve. That's about as simple as we're going to be able to get that to be in, a reasonably okay form to look at. You will want to memorize that just because it will make your life infinitely easier if they ever ask you to solve a logistic differential equation on the AP test. So if you are given dp dt equals kp times m minus p, and they will tell you in the problem the initial population, I mean, I would say almost 100% of the time they will tell you the initial population. You can go straight to this. Now, if they don't give you the initial population, if they say that after 3 years the population is 70, well, that sucks. Then you've got to go through and actually do this whole process with the problem and find the correct constant with it. But if they give you the initial population, this will work 100% of the time. Good or no? I know that took a while, but it's good practice with your algebra. Yeah. Any questions on that? At home? Any questions at home? Is the Zoom meeting still going?
No, I think we're good.
Okay, everyone's good. All right, wonderful. That's logistic growth. I think his name was Logistic. Honestly, I couldn't. I don't know who came up with it. Yeah. Yeah, then they were able to figure it. That is correct. I'm sure that's how it happened, but I could not tell you who it was. I could look it up. I'll look it up for you if you want sometime. All right. All right. Here's the problem. Let's do it. We got moose. Everybody likes moose, right? Mooses, mooses, meese. whatever they are. Maybe goose and geese, moose and meese. Mooses? Not gooses. I don't know. What do you guys think? Moose? I think the population of moose should be moose. I have 73 moose. Mooses? People at home? Anybody care?
The plural of moose is moose, according to the first thing that comes up in Google.
It's according to what?
The first thing that comes up in Google. So.
First thing that comes up in Google. I'm as good as the first thing that comes up in Google. All right. Should be moose, and it is moose. Nice. I like that better. We go from one moose to two mice. All right. So we got the growth rate of our population of moose, plural of moose. dt is 0.0003 p times 1,000 minus p. First off, what is the carrying capacity of the population? That should be the easy one. Carrying capacity is always M. It should be 1,000. Easy. Now, next very easy and important thing about the logistic growth equations is they will sometimes ask you, when is it increasing the most rapidly? When is the population growing most quickly? This is always 100% of the time at 1/2 of M. Always. Always growing the fastest at half of the carrying capacity. Okay. It's the point of inflection on the logistic growth rate. Okay. It's a point of inflection on the logistic growth rate. And I'll even write that point of inflection on the so that's a good thing to know for the AP test, that it is always increasing most rapidly and it is at half the carrying capacity, and that there is a point of inflection on the graph of P. Everybody good? Goodbye, whoever left Zoom. Somebody left Zoom and had enough for the day. Everyone good? All right. Now we want to solve this differential equation, given that the initial population of moose is 61. We have 61 moose to start. So we will just go in and we will use that wonderful formula that we had, rather than writing it as a differential equation and separating the variables and doing all of that. We will say that the population is equal to M, carrying capacity, 1,000, over 1 plus, what do we got? P naught over M minus P naught. And in fact, we're good at subtraction. What's 1,000 minus 61? 939. We can do that all in one step. Times E to the negative M K. In fact, let's do our multiplication all at the same time. 1,000 times 3,000 should be, just got to move that decimal over 3 times, right? And those aren't thousands today, another 10,000. Negative 0.3 T. And there it is. That's your equation. M over 1 plus P naught over M minus P naught E to the negative MK T. And if we wanted to find the population of moose at any given time, just plug in a T value of years. Sure. I have been requested to go back to the equation, so now I am. Oh. That was weird. That would all those sounds like. Yeah, P naught over M minus P naught. Let me make sure. Hold on 1 second. Let me make sure I didn't screw something up there. Okay. Yeah. Sorry, it's gonna be 939 over 61. I memorized my equation wrong. Just making sure we didn't screw that up. It'd be really cool if my toolbar was here so I could erase that. Sorry, that should be 939 over 61. Come on. It'd be really cool if I get my toolbar to show up. Oh, that made a circle thing like the toolbar is trying to show up. Still didn't show up. All right. I was just checking my notes from period 1 to make sure I hadn't made an arithmetic error somewhere in there. Let's see here. Let me see here. Why is this not? We're gonna fix this now. Of course. That'd be bad. All right. What was it? Not? Oh, I will in 1 second. What is it? 939?
Yeah, 939.
939. Okay. Sorry, I just plugged it into our formula. This doesn't. All right, sorry about that. I memorized my formula wrong over the last 2 seconds. Everyone good? Y'all good at home? Cool.
Nobody is responding.
This is where I was gonna make people, I used to make people do one without, and then we did this one to find the formula, but now we don't have to. All right, let's see if we can do this one. This one's a little bit more difficult because they don't actually give us that. Can you read it? I would close the door, but that's against the laws and they'll come and kill me. And the blinds. I guess I could close the blinds. That defeats the purpose of having the windows open. So what's the issue with this one? I'll give it an initial condition. But it's not written as dp dt equals kp times m minus p. It's p times something minus something times p. So we're going to have to factor out a k value, right, to make it into kp times m minus p. So what do we need to factor out here? Good. Everybody agree that we need to factor out this 3.125 times 10 to the negative 7? Yep. So if I do that, we're going to get the equation dp dt equals, we're factoring that out, it's going to be 3.125 times 10 to the negative 7 p times, and yeah, so you know, just divide the 0.1 by this, and that becomes what you say. Noah says that's 320,000. Everybody good with that? Y'all good with that at home? It's so much better when you interact and say yes or no.
Yes.
Yes. Wonderful. All right. Everyone's good here? All right. Cool. So what's our equation going to look like? Should look like is M. What's our carrying capacity? 320,000 over 1 plus, this time I'm going to do this right, M minus P naught over P naught. So our M is 320,000 minus our initial of 12,800, which is 320,000 minus 12,800. Should be 307,200 over our 12,800 e to the negative, and then we're going to have to put in our M times our K. Well, what's our M times our K going to be? That one we should know. We shouldn't have to do any arithmetic on that one. It should just be this 0.1, right, that we had up there originally. So 0.1. And obviously we want to reduce 307,200 over 12,800 a bit. And that's the basic formula today. Easy enough? Yeah. Anybody reduce that? 24. Wow. That's a nice number. Some person that really thought that'd be a good number. Right. Probably stole it from a textbook. In fact, I definitely stole it from a textbook. I don't know which textbook. I steal a lot of questions from textbooks. Then I don't have to make them up. Yeah. Everybody good there? We'll do one more. We're gonna have guppies. Yay! Everybody likes fish. Delicious fish. Probably not guppies. Ah, maybe they taste good. Not a lot of meat on a guppy though. Yeah, probably. Yeah. And I like fish. Like, huh, who knows? You guys want to just do this one entirely on your own? Yeah. Matt, you gotta do this one entirely on your own. All right, so first off, this one's already written in the form that we want. Starting as KP times N minus P. And we've got an initial population of 6. So we should be able to go through and just say that P is equal to our carrying capacity, 1 plus our carrying capacity minus 6, which should be 144 over the 150. What does that reduce to? Or sorry, over 6. What does that reduce to? 144 over 6. Would be 24. Another 24? Crazy. So 24 e to the negative, and then what's your k times your 0.225? So there's your population. How long does it take to reach 100? Well, you just plug in 100 and solve for t. And so I'm not going to go through all the steps. I'm just going to write it. What does C give you? 17.205. Everybody agree with that? These are weeks. You guys all agree at home with that? Everybody here is good with that?
Agree.
All right. What about 125? I'm not going to round out, but what did you come out to get for 125? Anybody? 21 by what? 278. Does that sound good to everybody? Anybody at home get that same value?
We agree.
You agree? Okay. Now, when it says how long does it take to reach its carrying capacity, how are we going to do that? Exactly. So the only way we're going to be able to do that is figure out when it rounds to be the carrying capacity. So we will set this equal to 149.5. That is the standard convention to find when it reaches the carrying capacity. So we'll say 149.5 equals 150 over 1 plus 24 e to the negative 0.225t. And that's how you will find when it reaches the carrying capacity. And it may ask you that on the AP test, when it reaches the carrying capacity, just use the closest value that it rounds to. Anybody get a value for that or no? 39.460. Yeah. Everybody good there? Just because that's the smallest number that will round to 150. And if we plug in 150, you try to plug in 150 here. When you multiply this out here, it doesn't work. Everybody good there? Yeah. Okay. And oftentimes they may ask you on the AP test, what, for these logistic difference equations, what is the limit as, they will say, what is the limit as, let's see, I had a good train of thought and then I lost it for a second. What is the limit as, t approaches infinity of dp dt? So they might ask you. So what is the limit as t approaches infinity of dp dt? What? Now for any general one of these equations, it should be the same. The limit as t approaches infinity of dp dt should be 0. Because we're thinking about this logistic growth equation, and the dp dt is the slope of the logistic growth equation, and we're approaching a horizontal asymptote, which is a slope of 0. So this is something they will often ask you, and then they will also often ask you the limit as t approaches infinity of p, and that one should always be. So these are two limits that they might ask you with regards to logistic differential equations on the AP test. Oftentimes they will just write out some situation like the guppies and then ask you one of these in the multiple choice. You might see that. Or it could be in the free response. Sometimes they do in the free response too. But you shouldn't have to really do any work with all numbers to figure this out. Does that make sense to everybody at home and here? Cool. All right. What do we think? That's it for logistic growth. We're done with Euler's method logistic growth. This is what the quiz will be on Friday. Stuff we did yesterday, stuff we did today. No review on the quiz, just Euler's method logistic growth. We've got 15 minutes. Would you guys prefer to work on the Euler's method and logistic growth problems and see if you have questions and want to ask, or do you want to just get quickly started with series? Anybody have a preference? Nobody here has a preference.
Series would probably be better.
What?
Series would probably be better because I know it's difficult. So I'd rather personally spend more time on series.
Series it is. We're going to do series. We're going to start our series. All right, give me 1 second to open that up. Okay, all right, so series, the fun thing that we've all been waiting for. This is the power series note in the Google Drive. Okay, so we talk about a series. A series is an infinite series. Okay? It's a sum of a bunch of terms of something that go on forever. They go on infinitely. A series is the first term plus the second term plus the third term plus the fourth term. Okay? It is a sum. That is what a series is. It is a sum of a bunch of terms of something. So there is that is the fundamental difference between a sequence and a series. In this class, we don't cover sequences, we cover series. And so a lot of people start out with the misconception that a series is just a list of numbers, like 1, 2, 3, 4, 5. That's an infinite sequence of numbers. But a series is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Or a series is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, infinitely. And a series is always infinitely. It always goes on forever. So what we may do as we work through this unit, and we will do a lot of times, is we will take a series and we will truncate it and cut it off somewhere. And we will call the piece that we've cut off a partial sum of that series. Okay? And so the series itself will be represented in a sigma notation form, just like this one. So this series, a sub 1, the first term, plus a sub 2, the second term, plus a sub 3, the third term, plus plus a sub n, the nth term, and so on, could be written out as the sum from k equals 1 to infinity of a sub k. Okay? So this is just a generic form of sum series, where a sub k is just some term. So I might write out a series that looks like the sum from k equals 1 to infinity of k. Well, we've dealt with things like this when we were converting between limits and stuff into integrals. Remember doing this, right? We should have a basic understanding of it. This should look like the series 1 plus 2 plus 3 plus 4 plus 5 and so on, right? Or we might have the sum of something like 1 over k. Okay? And we're also going to, use k. Okay. We also might be using n down here sometimes. But 1 over k would look like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. Everybody good with that? Okay, cool. So when we talk about these partial sums, we just talk about s sub 1. The first partial sum is just the first term. The second partial sum of our series is just the first 2 terms. The third partial sum is sub 3 is just the next 3. And so the sum of any finite number is the partial sum of the first n terms. But if we sum all the way to infinity, that is the full series by itself. Okay? Good? Everybody here seems good. Everybody at home good? Except for the 2 people that have left already.
Good.
Okay, cool. So that's just sort of grounding ourselves in what is a series. This is a series. A series is an infinite sum of a bunch of terms of things that are related in some way. Right? It could be k, it could be k squared, it could be 1 over k, it could be 3k plus 7, it could be, x minus 3 to the n power times n plus 1 factorial over n squared. It could be all kinds of things, right, that are somehow related. Okay? That's what we're going to do. So if the partial sums that we get, if we add up each partial sum, if that sequence of numbers of those partial sums comes out to be some number, if it has a limit as n goes towards infinity, then that tells us that the series converges to some value. So some of these series, some of these series, I think the plural of series is series, just like moose is moose. And I think, yeah, I think that makes sense. Yeah, maybe. I don't know, something. Anyway, these series will sometimes converge to a finite number. So we may say that, we may take like the series 1 over n squared. That series converges to a finite number. In fact, we will be able to prove that at some point, but we looked at that the other day with the improper integrals, right? This series, though, 1 over n, like we looked at with 1 over x with the integral from 1 to infinity, that one diverges. So some of these things, as we look at what happens as we go towards infinity, if we look at the partial sums, will converge to a certain value and some will not. We will use the term just like we did with integrals that were infinite, series that become infinitely large values. We also will say that they diverge. Right? They also diverge. Now, we're going to get a little bit more technical than saying, suppose we look at the partial sums of a series. If we look at if we're thinking about the one from k equals 1 to infinity of k, well, what do the partial sums look like? The first partial sum is 1. The second partial sum is 1 plus 2, right? 3. The third partial sum is 1 plus 2 plus 3, 6, right? And so on. These are not converging to a value, right? These are getting larger and larger and larger. So we would say the sequence of numbers 1, 3, 6 doesn't go to some finite value. Right? It goes to infinity. This series diverges. Right? The same would be true of 1 over k that we just looked at. It doesn't go to some specific value either. Right? But there will be plenty of series that do. And we're going to get a little bit more technical about it. Not a little bit. We're going to get a whole heck of a lot more technical about what makes a series converge and diverge. Because really, that's about 90% of what this entire unit is going to be about. Is when does a series converge and when does a series diverge? And one thing that we can be guaranteed of, no, wrong page. Okay, no, never mind. We're not going to be guaranteed of anything yet. Let's look at these series. I thought I had another page in between. But let's look at each of these infinite series. Okay. This one, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 is an infinite series, right? Could we write out a form for this? This is the sum from n equals 1 to infinity of, let's start at n equals 0, just for fun. That'll make our lives a little easier. How could we write out this series? The negative of 1? Okay. Wouldn't this be negative 1 to the power of n? What's negative 1 to the 0? 1. What's negative 1 to the 1? Negative 1. What's negative 1 to the 2? 1. What's negative 1 to the 3? Negative 1. Note, very important point here. Negative 1 to the n makes any series split back and forth between positive and negative terms. This makes the series alternate. We call this an alternating series. Okay? Not just 1 minus 1 plus 1 minus 1, but any series that goes back and forth between positive terms to negative terms, to positive term to negative term, we say that series alternates. And that's very important. Now, does this converge? Let's look at the partial sums. What's the first partial sum? 1. What's the second partial sum? What's the third partial sum? What's the fourth partial sum? Is this going towards some number? No, it's going back and forth between 1 and 0, and 1 and 0, and 1 and 0. It is not converging to some number. This diverges. Is this the only way we could have written this series out. N equals 0 to infinity of -1 to the n. Now, I could have left this number down here as n equals 1. In fact, this number down here is called the index. N equals 0 is the index. And I could have written this as the sum from n equals 1 to infinity of -1 to the n. Well, n minus 1 would work, right? Or, yeah, -n would probably work. N plus 1 would work. Right? N plus 3 would work. N minus 101 would work. Right? Any of those would work. Right? Plus, that'd be fine. So there's multiple ways to write out different series. So that's something we're going to have to get used to also. Okay? What about this one down here? Let's look at the partial sums real quick. What's the first partial sum? 0.3. What's the second partial sum? 0.33. What's the third partial sum? 0.333. I think we can see a pattern here. What's going to keep happening? Each time it's going to go 0.3333, 0.33333, 0.33333. And it's going to keep adding a 3 on that. And so this is going to converge, and it's going to converge to a value of 0.3 repeating. True? Which would be 1/3. So we have one series that diverges because the partial sums don't reach a specific number. We have one series that converges because they do reach a specific number. They go towards 1/3. And this one could be written out as the sum from n equals 1 to infinity of 3 over 10 to the n, right? And it converges to 1/3. So that's the very basic introduction of what we're going to do with series. We're going to start talking about geometric series tomorrow, which is, we really only deal with geometric series and power series. We're going to start with geometric series. We don't deal with arithmetic series. You guys have heard of arithmetic series probably before. Maybe not. That's fine. Whatever. Arithmetic series and geometric series, and then we're going to deal with power series. But we won't talk about arithmetic because they're boring. All right. That's it. What is what? Series can do everything. I'm not gonna answer. Okay, the question was, what can series do? They can literally do anything. They can literally do everything. Everything. I can't answer it because I need you to be awe-inspired and awe-struck in the next couple of days. I won't answer it now because you're gonna be so astounded and amazed. Well, that's lame. All right, have a wonderful day.